So let's look at a numerical example here. There is a round bar of 15 mm diameter which is subjected to a tensile force of 10 kilonewton, and the length of the bar is 200 mm. Right? He is asking us to find out the strain energy per unit volume, small u. Right? We have just now discussed strain energy per unit volume is nothing but the resilience, right? Or strain energy density, what we are referring to, strain energy and total strain energy. So he is asking finally what is the total strain energy developed. So here the value of elastic limit also given, right? And Young's modulus was also given. So that was the given data, and this is a direct substitution. It's a very simple problem, but we have to keep the things in the proper order. So let's look at the things that are required for us and what was with us. Strain energy per unit volume, right? We know the strain energy per unit volume value, right? What is that we have calculated? It is represented with a symbol, say small u, and you can write that in either in terms of load of px, or you can write in terms of stresses sigma square by 2e, or in terms of strain e epsilon square by 2. Any one of these forms you can write. Okay, so here for this what is required for us, Young's modulus was given, right? So and the load was given. So if you want to use this, load was given. Okay, then any other, we don't know that deformation how much it has undergone, that was not given, right? Or he has not no given mention any stress, but we can calculate because the load was given to us. So let's look at the to look at the complete view of the solution. Let's see what was given. So it is the diameter given. From the diameter, diameter is given means cross sectional area known to us, because it's a rod, a bar, a circular rod, a round bar. So the area is known to us, and length of the bar given and area was given known to, means that means we can know the volume of the bar, right? So now we know the area and volume, right? So and load was given. So once the load was known and area was known, we are able to calculate the stress, because stress is nothing but load by area. That means we are close to this one. So using this formula, out of this any one you can use, but this is more no, we come to the conclusion that this formula can be readily applied. So sigma square by 2e. So straight away you can apply. So load is given, the load value is how much? 10 kilonewton was given. Load 10 kilonewton, you convert into newtons, right? 10,000, right? 10 into 1000 divided by the cross sectional area, right? So the cross sectional area pi d square by 4, that comes around 176. You can substitute that. So 56.59. So this is the stress, right? Here we can check that whether it is exceeding the elastic limit or not. If it is exceeding elastic limit, that comes under the plastic region. So our strain energy will be calculating only in the elastic region. So it is not, no, it is less than the elastic limit. So we are on the right track. So now we can use that particular value to get the values of the strain energy per unit volume. So the strain energy per unit value, straight away you substitute. So there is no, we don't have put any, everything is known to us now. We got a clarity of solution. We just know the sigma, we know the anyway this modulus was given, that was given in straight away Newton per mm square. So that was also given, right? The information that we can write one more factor here is e, that was also given. So that substitute that, you will be getting the solution. So strain energy per unit volume represented by small u is nothing but, you can write either f or sigma, doesn't matter. So that we have calculated 2 times the value of the Young's modulus of elasticity, which was given 210 times 10 into 10,000 Newton per mm square, right? So by substituting that, no, you will be getting the solution right here. Sorry, you got the solution here. This is the solution. So if you want total strain energy, that is simply, no, what is the difference between strain energy per unit volume to strain energy? You simply multiply the strain energy per unit volume with volume, you will be getting the strain energy. So simply multiply. Area is known to us, right? In the beginning we got the area, right? Area and volume also, sorry, area and volume both we got. This is the volume. So you can simply multiply with the no uh, volume, you will be getting the total strain energy. Straightforward problem. So let's look it in the similar lines. Let us look at the one numerical example on shear. Here one point we have to remember is, when you are dealing with the shear loads or shear stress, there is not much difference on the formulation. In place of F or sigma, we are referring to, right, normal stress or direct stress. But when you are using a kind of shear load, the corresponding stress is shear stress. So only in place of uh, a sigma or F, you will be using that. Rest of the formulation remain as it is. That means strain energy due to shear stress is nothing but tau square, right, by, instead of what you call uh, Young's modulus, corresponding modulus here is the shear modulus. So tau square by 2z into volume you will be getting. Okay, same thing here also. This also can be written either in terms of stresses, or you can in terms of strains, or in terms of load even, right? So this is the formulation for shear. So let's look at one numerical example based on that. That is strain energy due to shear loads. Let's look at this problem. A rectangular block was given with dimensions of 80 by 60 by 40, right, fixed at the bottom edge. There is a bottom edge fixed, and we are applying a shear stress on the top surface. The total amount of the shear force is around 240 kilonewton at the surface as shown in the figure. So considering the shear stress proportional to the shear strain, now he is asking us to calculate these quantities. What is the shear angle, what is the shear strain energy volume per unit block, and total strain energy given is modulus of rigidity, that was also given for the calculating these quantities. So let us look at what are the unknowns and knowns in this problem, and put the things in the order so to get these no unknowns. What we are supposed to calculate is the shear angle, which is nothing but shear strain, right? So shear strain or shear angle both are same, and shear strain energy volume, shear strain energy per unit volume actually. So what you will be getting, shear strain energy per unit volume is nothing but previously we calculated, right? Shear strain energy, no, strain energy density, right? And finally total strain energy, right? So the formulation for this phi, if you want to get the phi, what is the formula associated with this phi? We can get from the basic understanding of stress strain. Phi is nothing but tau by g. Tau by g is equal to shear stress by shear modulus. Shear stress by shear modulus is your phi, right? So we know the g value given, and if you know this, you can get the no shear stress, then we can get the shear strain. So how to get the shear stress? We have been given load. So look at the information given. We have been given the shear force load, right there, from there, and of course you got the area with us, and which area you have to take. See, look at this shear stress or force is acting in the in this region. So this particular area only you have to take 40 by 60. This top area on this surface only it is acting. So the tangential area we have supposed to take. So 60 times 40, that is, this is the value, and you got the shear stress now. So what is the difficulty in getting this phi? Phi is nothing but tau by g. G is the standard constant value given, supply to us. So you can straight away find out the value of the shear angle. Look at the second one. What was the formulation for this? Shear strain energy volume per unit plane. That means strain energy density is asking us to find small u. But here due to not axial load but due to the shear. So what is the formulation? Like in the previous case we have written the sigma square by 2e, here it becomes tau square by 2e. So use that formula. And finally you multiply that with volume, you will be getting the total shear strain energy. So let's look at that solution. So whatever has been discussed now, it is shear stress we know, right? Just now calculated, right? Shear stress is nothing but load by area, that is 100. You take that value divided by the value that was supplied to us, the shear modulus, you can take that. Then you got this, okay, the shear strain. Then shear strain energy per unit volume, that is no, q square by 2z, right? Just as sigma square by 2e, this becomes q square by where shear, q or tau both all representing shear stress. You can use any symbol, doesn't make much difference. So use that, then you multiply that with the volume of the black, then you will be getting the total shear strain energy. So that's all about the topic on the strain energy due to axial and shear loads, right? Thank you.